This is on material characterization using correlative microscopy and artificial intelligence. And we have two speakers, Dr. Carlos Viol Barbosa and Dr. Jan Neumann. And I shortly introduce our speakers. Dr. Carlos Viol Barbosa is the CEO of Sciencedesk here in Freital, near Dresden. He holds a PhD in physics from the University of Trieste in Italy. And he worked for the Max Planck Institute, or for several Max Planck Institutes in Dresden and Halle, and for the Fraunhofer IVI, also here in Dresden. And the second speaker is Dr. Jan Neumann. He's a CEO and co-founder of NenoVision, and he holds a Master of Engineering degree in Engineering Physics and Applied Physics from the Brno University of Technology, and a PhD in nanotechnology from the same university. And now we are looking forward to your presentation.
Yes. Hello, everybody. Thank you very much for a very kind introduction. I will just I'm sorry. Oh. Oops. Yes. I'm sorry. Can you see my screen now?
Yeah, we can see the.
Okay, perfect. So once more, thank you. As was mentioned, what we will talk together with Carlos Barbosa from company Sciencedesk, we will talk about the material characterization, especially using the microscopy techniques. And we will see how there is a need for artificial intelligence and data processing to be able to really fully characterize the materials in the nanoscale. I will just shortly introduce what we are doing as a company, NenoVision, as we are from the Brno, where it's kind of the mecca of electron microscopy. So what we did, we developed the special module. It's an atomic force microscope, which you put inside the electron microscope. This is what you see on your image. And then we try to combine both techniques together. So we are trying to merge the forces of AFM and SEM and bring the additional value from the data characterization. Why to combine these techniques? Because the reason that the analysis in the nanoscale, it's quite complicated. So AFM and SEM are, I would say, one of the most common techniques which are used for such a characterization. AFM is enabling some parts, which is, for example, very precise analysis of 3D topography, or you can measure mechanical, electrical, or magnetic properties at sub-nanometer scale. And there are advantages of electron microscope, which is really fast 2D imaging, but you can also perform the chemical analysis, or you can modify the surface. And with our approach, with our product Lightscope, we combine everything together, AFM and the SEM. I think the best way would be just to show you a short introduction video where you can see also how it looks like and what are some of the applications. I'm afraid. Okay, now. Yeah, so it was a short intro about our product, and now I'd like to very quickly highlight the key advantages what we are offering. So the first of all, it's a complex and correlative sample analysis. So what does it mean? That in the nanoscale, we are capable to analyze the same area by the different techniques and then analyze the properties. So we know the chemical composition, we know the topography, we know the chemical, mechanical properties, all of this on the same area, and then we combine it. And as you can see, there is a many different data in spectroscopy, microscopy. So there is a need to work with the data and be able to analyze. And this is exactly the reason why we need artificial intelligence. And we are discussing and cooperating with the Sciencedesk and the Carlos. The second advantage is that during such analysis, which we are showing, you do everything in situ and the same time, under the same condition, and on the same place. So all of the characterization is done together. And the third advantage is that you can very precisely localize in the nanoscale the area which you would like to analyze. So what you see here, it's an AFM, very sharp tip, navigated to the specific location. There is a plenty of application areas. Mainly, it's a R&D or the development. So it's a material science, different nanostructure analysis. We have several applications for semiconductors where we can, for example, measure the current leakages in the transistor or do the different failure analysis, but we have also application in the life sciences. What I would like to highlight a bit of more is a correlative data acquisition, generally correlative analysis, because what you want to do, you want to analyze the different modalities by the different techniques, and you want to combine everything together. So with our unique approach, CPAM, we have developed the technique which we can simultaneously acquire the data from AFM and SEM, so acquire the different modalities, and then very nicely correlate them together. So the precision and the time efficiency of such an approach, it's uncomparable to operation with separated systems. So what we are doing, we are taking the best from both techniques. From AFM, we take very precise topography from the sample. From the electron microscopy, we take the contrast and information about topology, and then we very precisely correlate and merge all informations together. This is what you see in the CPAM view, as we call it. So the color represents the contrast from the SEM topography. High precision topography is defined by given by the AFM. And here's another example. What's the cutting edge and difference that if we simply measure only with the AFM, this is what you get, topography. If you add there additional information from the electron microscopy, this is the information and value which you are getting from your sample analysis. With our special approach, the advantage is that we simultaneously acquire many different data. And so this is what you see here on this small video. Within our software, we are collecting AFM, SEM, different SEM data, and then we can very nicely correlate them, all of them together. As I mentioned, we need some advanced image processing, and we are starting to use the artificial intelligence. And here I would like to show you one example. So we automatically correlate the drift, which sometimes happen when the SEM electron beam from the SEM is moving. So we'll train the network in the way that automatically we are able to correct the images to fit the images from the SEM and from the AFM. So if you have a look, if we combine both images together and correlate them using the drift correction with the artificial intelligence approach, we are automatically able to correct the errors coming from the instruments itself. So this is the original image. This is automatically corrected image. So with that, I would, and here's also result if we put it in 3D. So there is a huge improvement of the final analysis that you see how perfectly the images both are fitting together. So this is how we use correlative imaging and artificial intelligence together. Just to quickly sum up, we are dealing with the two microscopy techniques which we combine together. We have a quite unique approach how to measure and analyze the data. And now I will pass the word to Carlos, who will talk about the artificial intelligence part and actually how they are able to work with the microscopic data in order to improve the characterization of the sample. So thank you very much for your attention. I will be there for a question, or just contact us, visit our web pages to get more information. I think we have really plenty of things to share with you. Thank you very much for your attention. So now, yeah.
Cool. Well, thank you, Jan. I'll take over from here now. So in the second part of the presentation, I have two goals. My first goal, give a hint how Sciencedesk developed and implemented the solution of the automatic correlative image analysis. After that, if you still have time, I would like to say some words about the two software tools that we are developing that can help small and medium companies or even research organizations to implement and effectively use AI solutions at low cost. Okay, some time ago when I met Jan, he introduced me to the challenge of image correlation, this amazing tool that he has. And in that first time, he synthesized this challenge using the following question. Carlos, how can you match these two images? You have AFM on one side and STM image on the other side. Well, when I see this, I say, okay, it's very simple. Have just to find features, what is common, and overlap these common features. Then, at first glance, it looks like a classical image registration problem. So you have image registration when you have to stitch photos together, when you have to align some picture inside another picture. And it's a common issue for magnetic resonance image, where the technician needs to align consecutive slices of a 3D solid. Okay, then we have also standard methods. We can use feature descriptors. It's very common for photos, no? Where there is out-of-box algorithms that extract the fingerprints of features and try to combine these fingerprints. Most of the time based on local gradient of these features. A more modern approach would be using artificial intelligence, convolutional neural networks, or spatial transform networks. This last one performs really well for magnetic resonance. It managed to adapt to a small difference in the shapes of the cross-section of the image. Okay, it seems at first look that it should not be difficult. Now you can go use some textbook solutions or some modern application that you have for magnetic resonance. That's it. Well, however, you have to remember these images are produced for two different techniques. It means first, there are features that will be present in one image that will not be present in the other image. So they are measuring different things, topology and chemical contrast. Second, that is also very important for us, these AFM SEM, it seems they have very distinct local gradient profiles. This is something technical, but what I can say now, it is very difficult to make the previous methods work well in this scenario. Therefore, we had to come out with the original solution. And we were inspired in the autoencoder networks. In other words, autoencoder network is a convolutional network that copies the input to the output bottleneck. And a positive side effect of this is that it managed to extract essential features of the image because it needs the essential features to reconstruct the image later. We use this concept to build our solution. In this slide in the middle, I have this drawing in blue that represents an autoencoder-like topology of neural network. On the left I have input, and on the right I have the output. A common scenario for autoencoding would be we have the output being met in the input is the image. But we did something different. We inverted this. Now you have a same image being mapped in AFM and vice versa. The interesting thing here is when you do this, you create a machinery that manages features between these two images. And this is the way that you manage to detect this common features. You enhance the common features and then overlap them. That's here is the offset that was calculated, no? Automatically. And you see that it fits perfectly for the AFM image. It is this simple image, but in case where the object is more complicated, no? Again, this is one object matched to two different techniques, and how to match this image, how to correlate this information. In the output, you can see that still it managed to correlate so different. There are common features that are really hidden. I have to even highlight for you. So you can see here and here. So he managed to find these common features and correlate the two measurements. So finally, we have the for this challenge autocorrelation of AFM and SAM. The next step is how to implement the solution. And we did this using our software, trained in Neuron's microserver. This is a software that goes installed in a PC board, and then you can plug this to your device. So the concept is very simple. You have the software, that is a server, that goes to a PC board, an industrial board, and then is plugged to your device. As when you add any AI solution here, even as a plugin, it will be available to your device, very simply. I just want to say one word about this board here. We are using this UP Extreme. This from a young company. I find this very, very powerful. In this use case here, you see how versatile is that. You can plug the board in a camera and the movies, and the camera person are able to see visual effects of the chroma key in real time. So it's very impressive. But we are not doing movies, we are doing science. In our case, we have this PC board with the 3D neurons installed inside of the light scope control unit. The light scope is the NenoVision microscope. And then to update the versions of the AI solution through the trained neurons. There are several advantages in this approach. The first one, you reduce the integration cost, since the engineers of NenoVision don't have to adapt our AI code to their device. Second, it allows us a fast development and prototyping. You can test different solutions, add new features, just by interacting with the trained neural software. And third, being a microservice architecture, you have complete isolation of the system. If something can happen wrong in the AI solution, the AI code, in the processing, this is not going to interfere with the delicate good work of the microscope device. This was already mentioned in the first talk today. I have to stress that this beautiful solution was only possible because we have this merge of the data science knowledge with the field expertise of the people from science, the team of Sciencedesk and the NenoVision. And I really believe that this merge between data science and field expertise is necessary to produce real-world solutions in AI. Okay. In this last minute, I really would like to say some words about our software tools. Let's go very fast. The first one is trained neurons, is a microservice for embedded AI solutions, more focused in instrumentation and metrology. Yeah? I have already said some words. The second one is our research data automation. This is for failure analysis labs, research labs that enable them to use AI very easily. Basically, this is a sample and file management that has the capability of processing data. And you can do many things. You can, for instance, automatically label images from microscope. You can automatically count objects in these images. You can find some special mathematical patterns in spectra. Now, you that have thousands of them. And everything can be done through the interface. Like if you have some problem, you have just to up to an interface, set the AI algorithm, and press run. And then the system, you go to run all your files through this algorithm and save the output and index them with the sample and file. So in short, this is a very convenient tool for you to employ AI solutions today. No, like don't have to wait much. And they can use also performance, clusterize information, make segmentation of image. And if you have any problem, but you don't have a scientific programmer in your team, you can always count on Sciencedesk expertise in material science to provide an algorithm for your need. So this, I thank you, and I look forward for your questions.
Thank you very much for the very interesting presentation. And we have indeed questions. And I start with the first one regarding sample size. So which sample size is analyzable at the moment at your CPEM?
Yeah, hello, thank you for a question. So this is basically given by the SEM capabilities. We are basically working with 1 by 2 centimeter samples. And the area which we are able to analyze and measure together is given by the AFM. It's a 100 by 100 microns. So this is the scan range, which can be done together, but using the SEM, you can choose the different locations and then proceed the CPM analysis separately.
Okay, thank you. And there is a second question, higher rated than the rest. I think there is a sample preparation necessary, of course, prior measurement. So what do you have to do for that, for the preparation of the sample?
Not really. If you are using the electron microscope, that's it. So you are working with the traditional way as samples preparation for the electron microscopy. This is the bottleneck, I would say.
So the common way, so to say.
Yeah, common way. We are just the adapter.
Okay, thank you. Last question here. So I found the medical applications for CPM especially interesting. Is there already a concrete clinical use already, for example, in the cancer research or things like that?
So thank you very much for that. I was not aware. We did some sample analysis with the biologists, with some cells, etc., but not the clinical research. So if you don't mind, I will contact you and I would be really happy to discuss this opportunity.
But would be a great application, I think.
Yeah, definitely.
Okay, gentlemen, thank you very much for the very interesting presentation and the answer to the questions again.